Quantum computing. Three major hurdles to mainstream adoption. Imagine a future where quantum computers revolutionize industries, solving complex problems at lightning speeds. But hold your horses. Before this quantum leap becomes a reality, three major hurdles must be cleared. First off, let's dive into the technical challenges. Stabilizing qubits, the building blocks of quantum computing, is akin to walking a tightrope. These delicate entities can only maintain their quantum state for microseconds before environmental factors like heat, vibrations, or electromagnetic fields disrupt the show. To combat this, researchers resort to extreme measures, like chilling qubits to near absolute zero temperatures, or isolating them in vacuum chambers with laser assistance. Not exactly something you can order online. Scaling qubits is another beast altogether. Current quantum computers boast anywhere from 50 to 200 qubits, with IBM's Condor leading the pack with over 1,000. However, experts suggest that truly impactful quantum computing requires a staggering 10,000 to over 13 million qubits. And let's not forget the software conundrum. With limited quantum-compatible applications, aspiring pioneers face the depressing task of developing their own software and infrastructure. But wait, there's more. Beyond the technical realm lie societal and cultural barriers. The skills gap looms large, with McKinsey analysts projecting 3 quantum computing job openings for every qualified candidate in 2024. This talent shortage could delay progress for smaller enterprises hoping to lead the charge. Moreover, the high cost and complexity of quantum computing raise concerns about technological inequality. Will the power be hoarded by well-funded entities, leaving the less fortunate behind? Businesses eyeing quantum computing must also grapple with substantial infrastructure overhauls. While quantum computers won't entirely supplant classical counterparts anytime soon, significant investments are necessary to harness their potential. Cultural resistance may also arise, especially in sectors where quantum advantages are profound. Lastly, the security landscape shifts dramatically with quantum computing. Capable of cracking today's strongest encryption, quantum computers pose threats to state security and personal privacy. Safeguards must be established before these powerful machines go mainstream. Amidst these challenges, AI emerges as a potential savior. By accelerating common algorithms and boosting data processing, AI can expedite quantum computing advancements. Conversely, AI techniques like reinforcement learning can optimize qubit stabilization, while foundation models propose novel materials for stronger quantum machines. This AI quantum synergy might just crack the code to quantum supremacy. In conclusion, while technical hurdles will eventually succumb to innovation, businesses aiming to capitalize on quantum computing should address societal and cultural obstacles. By focusing on these aspects, organizations can pave the way for a quantum future without relying on tech giants' deep pockets. After all, solving these challenges is crucial for long-term quantum success. Quantum computing, the game changer since fire. Bank of America's $2 trillion forecast. Quantum computing isn't just exciting, it has the potential to redefine human civilization. Could it really match the transformative power of discovering fire? Analysts at Bank of America suggest it could, calling it the biggest revolution since harnessing flames. But here's where the debate heats up. Does this emerging technology truly deserve to be grouped with humanity's most foundational achievements? Imagine a world where complex calculations that now take decades are solved instantly. Quantum computing isn't just a step forward, it's a leap into the unknown, promising to solve problems humanity hasn't even fully articulated yet. The analogy to fire isn't arbitrary. Early humans discovered that controlled flames to cook food, ward off predators, and eventually smelt metals, stepping stones to civilization. Similarly, quantum computers could unlock mysteries of material science, pharmaceutical breakthroughs, and rewire logistic systems. But the catch? These subatomic-powered machines aren't just faster, they're fundamentally different. While classical computers work like digital calculators, quantum processors leverage the weird science of entanglement and superposition, a realm where particles exist in multiple states at once. This isn't evolution, It's revolution. Here's the trifecta of opportunity. 1. Solving drug discovery challenges through molecular simulations. 2. Creating indestructible materials. And 3. Reinventing encryption. But wait, there's a speed bump. These qubits, the quantum equivalent of bits, are notoriously fragile. Their sensitivity to environmental noise, like temperature fluctuations or stray photons, means even minor disturbances can derail calculations. This isn't a minor issue. It's why current systems, like Google's Sycamore processor, can perform mind-boggling tasks, like solving a problem in 6 seconds that would take 47 years on the world's fastest supercomputer, but haven't cracked real-world applications yet. The Willow chip took this scalability to its zenith last December, solving a problem that would have taken 10 septillion years for classical computers. But these showstoppers still mean little in practical terms. They're benchmarks, not medicine cabinets or fortified materials. The AI connection adds another layer of intrigue. Generative AI could optimize quantum algorithms, while quantum computing might accelerate AI training, potentially creating a feedback loop that pushes both fields forward. BFA dreams aloud about artificial superintelligence, though this remains speculative. But here's the cultural elephant. When NVIDIA's CEO Jensen Huang dampens expectations by saying quantum won't be better at spreadsheets, he's not dismissing its importance. He's reining in the hype. His prediction that breakthroughs are decades away clashes with today's rapid developments. Think of it as a volume knob analogy from Quantum Circuit's co-founder Rob Shulkoff. We're gradually cranking up the dial, hearing faint melodies now with full orchestras to come. The real challenge? Patience. But let's talk geopolitics. Whoever dominates this field could rewrite the global power map. The US currently leads in computing power, but mastering quantum could redistribute that advantage overnight. China, Google, IBM, each player is racing to control the next frontier. The stakes? Economic dominance, military supremacy, and stolen technological thunder. But here's the question. Is this a race or a collaborative odyssey? The answer will shape our collective future. So, does quantum computing truly rival fire's significance, or are we inflating its potential in the excitement of innovation? On one hand, fire unlocked civilization. On the other, modern tech often lacks that primal need. But if quantum delivers on even half its promises, now medicines, sustainable materials, unhackable communications, it would be a game changer. The catch? Timing. Experts warn the most transformative applications, practical quantum advantages, remain a decade plus away. Until then, we're left with questions. Will this technology prove a silver bullet or a mirage? And what happens if another civilization gets there first? Gather your thoughts, then join the debate below. Should we bet big on this digital fire or proceed with caution? Share your perspective, because the future is being written in qubits right now. What is quantum advantage? IBM and Pascal's measured path for the future. Quantum leap or hype? Scientists chart a clearer path to quantum supremacy. Imagine owning a computer that could solve problems no classical machine can touch. But how do we even prove it works? This isn't sci-fi. A groundbreaking new study from IBM and French quantum startup Pasqal proposes a concrete framework to define and demonstrate quantum advantage, the holy grail where quantum machines outperform classical systems by measurable margins. The problem: trust. Quantum computers don't need better algorithms. They need ways to verify their answers. Traditional methods often leave outputs that can't be checked, creating a paradox. If you can't simulate the problem classically, how do you know the quantum result is right? Researchers attack this challenge through 3 practical strategies. Fault-tolerant guarantees. For now, these remain theoretical, requiring thousands of qubits, but they're the gold standard. Self-verifying tasks. Tasks like factoring large numbers produce answer formats that are easy to confirm, even if generating them classically is impossible. 3. Comparable estimates. Expectation values, like energy estimates for molecules, can be benchmarked against known results, creating an apples-to-apples comparison. The hot zones. The study highlights 3 problem classes where near-term quantum wins are most likely. Sampling showdowns, generating binary patterns from quantum circuits. While most are hard to validate, special cases like peak circuits create probability distributions where one outcome dominates, simplifying verification. Variational voltage tests. Methods like VQE, variational quantum eigensolver, estimate energy states. New techniques like sample-based quantum diagonalization, SQD, output noise-resistant classical data, making them easier to cross-check. Expectation exploration. Average-based calculations used in quantum simulations and machine learning. Errors compound here, demanding precise error mitigation strategies. But here's the twist. If they can produce outputs that match known benchmarks, that's a solid win. It's not about flashy breakthroughs, but incremental improvement over today's best classical methods. Why error matters more than algorithms? Contrary to popular belief, quantum progress isn't being held back by algorithm design. The bottleneck is error management. The study breaks error handling into 3 tiers. 1. Correction. Fantasy territory for now. Requires perfect qubit control. 2. Mitigation. Statistical tricks like noise extrapolation to clean results. 3. Detection. Real-time checks to discard corrupted computations. Hybrid quantum classical systems could bridge the gap, using classical post-processing to amplify noisy quantum outputs. IBM's Heron processor, 156 qubits, 250K operations per second, and Pascal's neutral atoms, scalable for both analog and digital operations, lead the hardware race. Controversy alert. Will future quantum wins depend on superconducting circuits or neutral atoms? Skeptics argue neutral atoms' analog operations can't scale, while proponents counter that their low error rates make them ideal for hybrid workflows. The quantum compute conundrum. Current hardware is noisy. Even with breakthroughs, the path to advantage leans heavily on heavy classical collaboration. The researchers proposed treating quantum chips as specialized accelerators, integrated into high-performance computing clusters via standard scheduling pools. The road ahead? Testing, not triumph. The paper ends with a sobering message. Quantum advantage isn't about ultimate victory. It's about falsifiable claims. Each reported win or failure isn't an endpoint, but a milestone to refine benchmarks. What do you think? Could hybrid systems achieve advantage before fault-tolerant machines? Should the field prioritize verifiable tasks over complex computations? Share your take below, and let's keep the quantum conversation alive.